There it is. So like I was already telling you, a tautology is a law of propositional logic. It's a statement which has all truths as its outputs. A contradiction, on the other hand, is a statement whose truth function has all falses as its output. In other words, a contradiction is a statement, missing a T here, whose negation is a tautology. Two statements are called propositionally equivalent if a tautology results when the connective, if and only if, the biconditional is put between them. Let's see if I got a... So here is a bunch of things we could prove. All right, so what would you guys like to try to prove here? These are all tautologies. Let's go with the law of non-contradiction, P and not P. That one's easy. So let's look at a proof of 2. So here's our proposition. Let P be a proposition. We've either got true, we got false, right? Then I want to look at not P as well. So that's what? False, true. So what I'm working on is building this statement up, all right, piece by piece. So I start with P. I got my not P. Now I need to do P and not P. That's my next column. I got to be careful, otherwise I'm going to run out of whiteboard here. P and not P. How's that go? True and false? False. False and true? False, right? So then what? Next step? Negate that, right? So when we're negating P and not P. And so how's that go? False becomes true. Oh man. Trying to write with the other end of the marker, that's not going to work. And false becomes true. Thus, not P and not P is a tautology. Tautologies are laws of propositional logic. We can always use a tautology to convert one thing to another. And that, you'll hear sometimes people will say, like, as a criticism of an argument, that's a tautology. Well, that's maybe a criticism that's valid for that particular use in English, but in math, tautologies are very useful. It doesn't mean you're not doing anything. Like, you're going to see in this class that sometimes proving an implication is rather difficult, whereas proving the contrapositive of the implication becomes simple for various reasons native to the problem. Yep.
I just have a question on the implication.
Sure.
Why would false implies true be true?
Because that's the definition of implication. So that is the definition of implication. Yeah. I'm sorry if that's, not satisfying, but it is the explanation. Okay, so let's see here. Let me make use of this. Let's do a few more while we're at it. I'm going to leave the not P and not Q up here. And we'll swap these columns out for something else. Well, let me just start afresh. That'll be easier for you guys to follow. Come on. I mean, you could ask the same thing about or, right? Like, why is or true when both are true? Mathematical or. That is why we're giving these definitions in terms of truth table, to erase any kind of argument about those things. This is oftentimes what's done in math. We take a common word and give it a technical meaning. In mathematics, there are no less than a dozen different technical definitions of the word simple. Like, you talk about a simple group, that doesn't mean you're saying the group is easy to understand. That means something technical about its structure. So this is a bad, well, I don't know, is a bad habit is a good habit. It's a habit, though. Okay, so let's look at a truth table and see what else we can learn. So we've got false, 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 true, true, false, true, true. And let's prove a few things. I'm going to be greedy. We're going to do more than one thing at a time. So this is going to be a big truth table. All right. We'll start out with P or Q. So P or Q is what? That is false, true, true, and true. Right? P or Q is mostly true. It's only false if both the inputs are false. Right? Let's look at not P or Q. How's that go? Not P or Q gives us what?
False, false, false.
Yeah, true, false, false, false. Very good. Right? Let's see here. What else can we do? Well, let's look at not P and not Q. We'll make those our next two columns. Not P, not Q. So not P is true, true, false, false. This is true, false, true, false. All right. So let us now look at not P and not Q. We don't need parentheses, right? What's the logical, or what's the order of operations here? We do the negations first, right? So how's that go? What's not P and not Q? True, false, false, false. Right? So you see what we got here? So we can write a sentence down here, thus not P or Q is logically equivalent to not P and not Q. Right? This one's important. It has a name. This is one of De Morgan's laws. Right? It's down here. We just proved number 7 part, the second part. All right? See, I could add another column here, right? I could add another column which is not P or Q, if and only if, not P and, sorry about that, not Q. Right? And this would be a very boring column, which would accomplish the same logical purpose as the sentence I just wrote, right? Because what would the truth values be in that? Yeah, true, 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 right? So, I'd like to erase that column for the sake of writing more interesting things in that board space, if that's okay with you guys. So, I learned that from Dr. Sprano. Let's see here. So, okay, so what else could we do? How about this? Not P. That's what? That's
False.
false, false, true, true, right? So what is that? This is by, I really should say, let's see here, 1, 2, 3, 4, 5, 6, 7. Comparing, I should really, it'd be better if I said comparing columns, what? That was comparing what? Columns 1, 2, 3, 4, 4 and 7, right? So if we're trying to do more than one thing at a time, it's probably good to label things and refer to labels, right? This, P, if and only if what? Not P, right? Comparing by columns, what? 1? And I got 1, 2, 3, 4, 5, 6, 7, 8, right? Those are the same in every case. That's a tautology. Another tautology we can form is P or not P. P or not P, how's that go? It's true. Right? This is the so-called law of the excluded middle up here. Right? The law of the excluded middle. Let's see here. One last story arc here for today. Suppose we have P implies Q. We also have Q implies P here. Right? And then my final column for today will be, I can't quite fit it in here. You have to, my bad guys. But this one we're going to do P implies Q and Q implies P. That's going to go here. So P implies Q is what? It's true except in what case? True implies false. So yeah, I know it matters. P implies Q and Q implies P are not logically equivalent, right? Like Q implies P, false implies false, true. True implies false, false. False implies true is true. True implies true is true. These two columns are not the same. So a conditional and its converse are logically inequivalent. Two statements are logically equivalent if they disagree on even one case, right? How about the conjunction of these two statements? P implies Q and Q implies P. What do we get there? True, false, false, true, right? Now, if I had more space to write, can you recognize what this is? Same as what? Biconditional. Yeah. So what does this prove if I want, I'm being a bad example right now because I like to write everything out in sentences and not leave things out, right? You should write everything out. I can't always write everything out in class, but I try to as much as I can. But this that we just did, so we have established the tautology that P if and only if Q is logically equivalent to P implies Q and Q implies P. So that's why we call it a biconditional, right? Because a biconditional is true if and only if the implication and its converse are both holding true. This comes up in proof after proof after proof we'll do this semester, where if we're faced with the proof of a biconditional, we've proved first the direct, the forward direction, and then also the reverse direction, right? So these tautologies that we're learning, they form the basis for like everything that we do. So anyway, thanks guys.